Okay, and then the last one is the bumper cars. This one starts out with, a little bit of kinematics. So we're told that a car up here, we're looking just at car A, has an initial velocity of 2 meters per second and a final velocity of 5 meters per second and an acceleration of 1.5 meters per second squared. And we're looking for how long it takes to travel the 15 meters. So one thing you have to be very careful is that it doesn't reach 5 meters per second at 15 meters. So we can't assume that it just goes from 2 to 5 with a distance of 15. It actually reaches 5 meters per second before even halfway. So the first thing we have to find here is really you could find one of two things. We need them both. We need the distance that it travels during this first phase going from 2 to 5. And then ultimately we need the time. So let's find the distance. So remember, v final squared equals v initial squared plus 2ad. They gave us nice easy numbers here. So 25, I'm being a little lazy here, minus 4 over 2 times a is 3, gives us a distance of 7 meters, right? So that means it travels, it gets to about right here, and now it reaches 5 meters per second, and now it travels at a constant speed for the rest. So that means we have 8 meters left at 5 meters per second. So to travel 8 meters at 5 meters per second, velocity equals distance over time when it's a constant. So the time would simply be 8 meters at 5 meters per second is 1.6 seconds. So this is going to take 1.6 seconds, but we still need to figure out how long it takes to get. So we need this t. So I can go right back in and say acceleration equals change in velocity over time. So time equals change in velocity over acceleration. So it went from 2 to 5, so it increased by 3 meters per second at a rate of 1.5 meters per second squared equals 2 seconds. So I put those together, and I get a total time of 3.6 seconds. So there's about a month, I guess, maybe a few weeks of kinematics there. It would be great if you could even draw maybe what the velocity time graph would look like for that motion. All right, moving into the collision part. So now let's read. It says this cart's moving at 2 meters per second. But remember, when this cart gets over to here, here's the bumper car A. So now it's moving at 5 meters per second. So we can forget about its initial condition at just before the collision. It's traveling at 5. Bumper car 2 is moving oh, sorry, bumper car oh, it's at rest. Sorry, I was looking forever for the initial speed of B, and it's at rest. So we can draw this out. Bumper car A strikes bumper car B, that's at rest. This guy is now moving at 5 meters per second to the right. It bumps it, and it says that bumper car B now moves to the right at 4.8 meters per second. And we're looking for what is bumper car A going to do as a result. So let's get these masses. A was 250, B was 200. So this would be 250 times 5. Has to equal, over here, 200 times 4 would be 960. So right away we can see that bumper car A has to be moving to the right because we don't even have enough momentum yet to equal bumper car A's momentum. So A had 1260 all by himself before the collision. So B only has 960 to the right. So I know that A has to make up the difference. So that means 1250 minus 960 divided by the mass of car A has to tell us how fast he's going afterwards. So 1250 minus 960 divided by 250 is about 1.2 meters per second to the right. It comes out to be a positive value, which also tells us it has to be to the right. And then lastly is this an elastic collision? Once again, if it's elastic, it's basically saying, is K conserved, right? That's what asking you if it's elastic. So we have to solve it out. Let's write these values in. This one's traveling at 1.2. So is it elastic? So we have 1/2 MAVA initial squared plus 0. So how much kinetic energy do we have here? We have all the values, so we can calculate that. 0.5 times 250 times 25 gives us 3,125 joules of kinetic energy before the collision. After the collision, we have two cars, so we have to add them together. Remember, they're vectors. It doesn't matter which way they're going. So we have 0.5 times 200 times 4.8 squared is 2304. So this guy has 2300 or so joules. And then car A, unless he needs to have enough momentum to balance out these sides, we've got 0.5 times 250 times 1.2 is 180, only 180. It's only about 2,500 joules. We started out with 3,125. So they are not equal. So this must be an inelastic collision.